This is Manoj. Welcome to the lecture. Today we are going to look at the following concept of probability. It's called Bayes' theorem. Before I jump in and formally define the concept, let's look at an example which illustrates the concept better. We have two bags, E1 and E2, containing red and green balls. E1 contains one red ball and two green balls. E2 has one red and three green balls. Let's consider a random experiment wherein you're asked to pick a bag from these two at random, and from the bag you've chosen, you're asked to pick a ball and say its name. Now, we have, from the earlier concepts we have already covered, we can say that the probability of occurring of E1 is half, probability of occurring of E2 is half, and we can similarly derive further probabilities. Now, suppose we say that we have already seen a red ball. Then what is the probability that the ball has been picked from bag E1? So let's look at it now. In order to derive that probability, let's have a tree structure of probability, which helps us understand the concept better. So we're starting with the sample space, the start of the experiment, and then you branch out according to the outcomes of the event. So the first step is you pick a bag from those two. With probability PE1, you can pick bag E1, and with probability PE2, you can pick bag E2. Then once you are at E1, you can either get a red or green. The event that you got a red from E1 is nothing but the event R intersection E1. Both R and E1 are occurring. Similarly, you branch out, you get probability that you got a green ball from E1. Similarly, you have the other probabilities. Now, if you look at the stems of these branches, they define the probability of that particular event. The one we have already said that there is P of E1 and P of E2. Then in the second level, you know that you have already chosen E1, so that the probability that you can get a red ball is probability of R given E1. So first you get a probability E1, and then you get a probability of R given E1. With that probability you end up at this particular event. Similarly, you have other probabilities, G given E1, R given E2, and G given E2. So if you want to write down the probabilities, this is half, since you can pick up both those bags equally likely. And this probability, once you are inside E1, you have one red and two green balls, so you can pick a red ball with probability 1/3 and a green ball with probability 2/3. And similarly, once you are in E2, you can pick up a red ball from one red and three green balls, that is 1/4 probability, and a green ball can be picked with a probability of 3/4. So at the start of this lecture, I asked you to define the probability that the ball has been chosen from bag E1 given red has already occurred. What is this? Now let's just write out the conditional probability of this, which is nothing but P of E1 intersection R by P of R. Now P of intersection R is nothing but P of R intersection E1, which is nothing but this probability into this probability. Also we can see that it can be derived from the multiplication rule of probability, which is nothing but P of E1, the first branch, then the second branch, that is probability of red given you have chosen bag E1. And what is the probability of red ball? Let's derive it. If you look closely, R is the probability of getting a red ball, which is nothing but probability of getting a red ball from E1 or red ball from E2. So of all these four outcomes, you can get a red ball when this or this event occurs. And since these two are disjoint events, the probability of union of these two events is nothing but probability of this plus probability of this. So I can say that P of R equal to P of R intersection E1 plus P of R intersection E2. This is nothing but this probability into this, and this is nothing but probability of this into probability of this. Also, we just use the multiplication rule of probability and say that this is P of E1 into P of R given E1 plus P of E2 into P of R given E2, which is nothing but, if you just substitute these numbers, it will be half into 1/3 plus half into 1/4, which will be half into 7 by 12. I'll just put it here, and your probability of E1 given R will be P of E1 into 1/3 by this summation, which is half into 7 by 12. This will be 4 by 7. So this 4 by 7 is nothing but the probability that the ball has been chosen from bag E1 given a red ball has been chosen. So okay, this is a small example. Now let's try to generalize this and formally define the concept of Bayes theorem. Let's consider a general scenario. Let's say we have n bags. Each of them contains some red and green balls, and we repeat the experiment just like before. You just choose a bag and then choose a ball and shout its name. Let A be the event that red ball occurs. What is the probability that the ball has been chosen from bag EI given that a red ball has already occurred? So let's come out of the ball bag scenario. In general, if we have n events which partition the sample space, which means they divide them into chunks so that they don't have any commonalities, they're pairwise disjoint, mutually exclusive, and they're collectively exhaustive. Collectively, they just span the sample space, and you have any event. Given such a scenario, you can always derive the probability of EI given A using the Bayes theorem. So let's try to write this probability. Using the condition probability, this is nothing but P of EI intersection A by P of A. Now since we have, we can easily define probability of E1, probability of E2, En, and probability of A given E1, A given E2, all of them. Let's try to put these summations in terms of those values. So this will be probability of EI into probability of A given EI into, let's derive this. If you look closely, A in this particular example is being partitioned, the sample space is being partitioned by these 5 events. Similarly, A is being partitioned with them. So this particular chunk is A intersection E1, this is A intersection E2, and similarly we have other things. So if you just add these tiny chunks and put them together, you get A. Let me just derive that. A is nothing but A intersection S, and S from above is nothing but E1 union E2 union En. So what we have is A intersection E1, A intersection E2, A intersection En, just the union of all of them. So that is what we have seen in the figure. You just add these 5 chunks, put them together, and you get A. So now notice that since E1 and E2 and En, they are all pairwise disjoint, so are these small events, A intersection E1, A intersection E2, and A intersection En. So from the addition rule of probability, what you have is, for these disjoint events, the probability of the union is nothing but the sum of individual probabilities. So it is nothing but sigma j running from 1 to n probability of A intersection Ej. So just apply the multiplication rule of probability to get P of Ej into P of A given Ej. So just that is P of A n of Ej into P of A given Ej. If you look closely, this thing we are trying to define, and we can easily define all of this. I mean, given EI, what is PA? Given EJ, what is PA? And what is PEIJ, PEI? Each of them are easily derivable. So this is Bayes theorem.